So today I want to have a look at joint distributions. Now, these are the same distributions that we've been looking at this whole time. So the densities, the mass functions, the cumulative functions, except we're just representing them in a higher dimension. So what do I mean by a higher dimension? So this is the case where we are modeling not just one random variable, but now we're modeling multiple random variables. So I guess it would be two or more, I suppose. In this case, we'll keep it simple-ish with just the two random variables, so we can visualize stuff a bit easier. But it's good to keep in mind that this can be applied to many, many more. So I'll start off with the cumulative function, and hopefully this will become a bit clearer as I write this down. So again, the cumulative function is distinguished by its capital letter, and we'll relate this now to two random variables, so the random variable x and the random variable y. Again, we could have more random variables here, but in this case I want to keep it simple with just the two. And because we're relating to two random variables, now we should have two inputs. So I'll denote them with the small letters x and y. And because it's a cumulative function still, it is simply the probability that the random variable x will be less than or equal to the past value small x, and that the random variable y will be less than or equal to the past in value small letter y. Okay, so let me just box that because that is that definition. Okay, so hopefully this kind of clarifies a bit what I meant by the sort of higher dimensional case. And now what we're going to do is we're also going to represent the density and mass functions. So now we use the lowercase letter f, again relating over the random variables x and y and similar inputs. And there are the two cases we've explored for the discrete and continuous case. So for the discrete case, this is the mass function. So it would be the probability that our random variable x is x, and that the random variable y is equal to the passed in value y. And so this is for the discrete case. Okay. And secondly, for the continuous case, we changed our frame of reference to probability densities or likelihoods, which I'll put here. So likelihood that our random variable x will be equal to x, and our random variable y will be equal to y. And so this is for the continuous case. Continuous. Okay, and let me box that again as well. So I'll go through an example as well because I think that they're quite useful. So let's say we have a set of people, right? Bob, Jim, Charlie, and Jenny, or whatever. This set of people, and we're going to randomly pick a person and get their weight and height, and we want to get some information or some conclusions based off these observations, and we want to model both of these things at the same time. So let's have a random variable x be a person's weight. So we've sampled a person from our set of people, and we'll put x as that person's weight. Okay, and we'll define a random variable y as the person's height. So you can see how we've defined the two different random variables now. And let's keep it relatively simple still and say that this is a uniform distribution. It's a continuous uniform distribution because we can think about how getting an exact weight or an exact height would be across a continuous range. So I'll define it here again as f. So this is the density function for these both of these random variables, and I'll do all the stuff in yellow first so that I don't have to keep switching around, and because it's a continuous uniform function, this will have a value c, a constant value c. And so again, we relate it to the person's weight and pass through that weight. And that, let's say that weight will be in the range, I don't know, 1 to 10. It's a bit arbitrary, but there you go. We don't really know what units these are. It's just in the range 1 to 10. And let's say that we also pass through a person's height, which will be in the range, I don't know, 1 to 5. I don't want to put 0 because having a 0 weight or 0 height seems wrong. But yes, this function will also relate to that y random variable or the person's height, and we also pass this through. So let's say we want to now get a value for c. I think it helps at this point to draw this function graphically. It'll be a bit challenging because it's in a higher dimension, but I think it's manageable in 2 dimensions. So we'll have the y-axis be the person's height, right? And we'll have the x-axis be the person's weight. Okay, and we said that the weight can go from 1 to 10. And we said that the heights can go from 1 to 5. Okay. So this covers the 2-dimensional set of possibilities, right? But now if we imagine a third axis, say, coming out of the screen, which would represent the probability densities, because this will be a 3-dimensional function, that there will actually be a plane across the relevant range set to a constant value c. So I'll repeat that again. Say that there's an axis coming out of the screen which will represent the probability densities of each possibility in this 2-dimensional range. And it will have a constant value c for the ranges that we've specified. So I'll even draw it here. So each of these points in this set that we've drawn here will have a probability density or likelihood associated with it. So outside of the ranges we've specified, it will be 0. So this point would have a density of 0. This point has a density of 0. This point has a density of 0, so on and so on. And equally up to this extreme, this point would have a density of 0, and so on and so on. However, in the range of suitable values that we've specified here, these will have densities of value c. So c, 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 and so on, and again over here, c. The values of the densities will all be c. So when we looked at the density function before, we said that we can check its validity by seeing if the probability over all the possibilities sum to 1. And we did that with the integration tool. And we can do the same thing here. So what we'll do is we'll say, let's integrate over the valid ranges of x. And I like to think about this kind of like a for loop, if you've ever done anything kind of computer science related. So I'll write the integration symbol here, but you can think of it as saying for the values of x in the range 1 to 10. And then nested within that for loop, for the values of y in the range 1 to 5. We want to kind of sum, you could say, the probability densities over those ranges, and get so this would essentially kind of be a volume. So again, kind of using a visualization, we have a cuboid here in this range, right? With height or with width 4, with length 9, and with height c. And we want to get the volume of that cuboid and check that it's equal to 1. So writing that with mathematical notation, we say we integrate over the valid x ranges or what we define as the length, and we integrate over the width and we pass in the height, and we say dy and dx. And again, because this ends up being essentially a volume, this will be, or the volume of a cuboid, it will be 9 times 4 times c, which is 36c. And again, we know that this value, which is the probability, the sum or the total probability over all possibilities, that this should be equal to 1. And so looking at this, we can see that we can rearrange it to finally get our value of c, which would be 1 over 36. Great. Now let's go a bit deeper. Let's say that we are going to sample a person and we want to check if their weight will be within a certain range and their height will be within a certain range. So let's define this statistic as PR. I'll put it here. And this will be the probability that the person's weight will be in the range 3 and 8. And not only that, but we will also define, we want to check, as well as this condition, if the person's height will be in the range, let's say, 2 to 4.5. Okay. Right. So we want to get this probability. So with similar logic to what we've said before, we can define this as the volume of the cuboid over the ranges that we've specified. So let me kind of visualize this further. Let's say that this point is 3, and let's say that this point is 8, right? So from our inequalities, we can draw these lines here. Okay, and equally over the y range, we've limited it to be from, let's say this is 2, and let's say that this here is 4.5, and we have a set of lines over here too. And you see we kind of end up with this region here, where I'm going to put diagonal lines across. We now want to get the volume over this region. So again, we can visualize this as this function as a cuboid, where the values, a cuboid with length 5 and height 2.5, or width 2.5, and then height c. So again, because it's a probability density function, we want to get the volume of that cuboid, and again we can do that with the tool of integration. So we say 4, we integrate over the range 3 to 8, but I like to think of it as almost saying like for that range. So for the range 3 to 8, and for the y range 2 to 4.5, we take that value c and we say with respect to y and with respect to x. Okay, and again, in this case, this is a simple volume, so we can put that down now, and we can say that this is simply 5, like I said before, times 2.5, times it by c. In this case, we actually know what c is now. We remember, we've calculated that before. This is 1 over 36. And this is 25 over 72. And there you go. We have found the probability that a person's weight will be between 3 and 8, and that their height will be between 2 and 4.5. And again, keeping in mind that this can be done for many more random variables, so this could be a almost endless list of random variables, and the way you would handle that is you could think about we would just simply add more axes to this graph. So say now that there was a random variable z, right, which represented, who knows, a person's nose length. I'm just making stuff up now, but let's say that was the case, and I'm just trying to find a suitable color. Let's say we had this variable z, which was like I said, nose length or something silly. Then you can think, or there would be an extra axis along this graph, which would be the z-axis, and we could get regions over a three-dimensional range and kind of integrate over a three-dimensional space, requiring another kind of for loop nested within the two we already have. And so yeah, hopefully that's made some sense. Let me know if you have any questions, and I'll see you next time. Thank you very much.